Hey, Vlad here, devinside.com, and welcome to another video. I'm sorry to interrupt the Scala playlist again, but we need some fundamentals to continue. In fact, even the next video might not be part of the Scala playlist. However, both this video and the next one are very much related to the Scala playlist. Now, quite a few times on this channel I mentioned that programming is not math. The time has come to have a slightly deeper conversation about this. First things first, if you're new here, you should probably know that a lot of content on this channel is going to be related to Scala. But if you don't know any Scala, then don't worry. We're not going to write much code today. So we're in Ubuntu in the virtual machine, and I have Sublime Text as my text editor on the left, and I have a regular terminal on the right, which runs SBT, which is a Scala build tool, which is going to build our code and run it for us. Alright, having gotten that out of the way, let's talk about functions. Every programming language out there has a concept of units of computation, and we use many names for them, like routine, subroutine, procedure, unit of computation, and we also use the word function, a term most likely borrowed from the field of mathematics. The whole computer science field was invented by mathematicians, after all. The thing is that in math, functions are strictly defined, but in programming they aren't. And those colliding naming conventions are contributing to the stigma that programming is all about math. So this is why I'm making this video, to debunk this myth a little bit. So let's see what the differences are between a function in math and a function in programming. And no worries, I'm not even going to try to define them. First order of business, naming conventions. Now, what I'm going to do now is I'm going to pretend like I'm writing math over here, so I'm going to write some pseudocode. So let's say that we have a function that takes an x and is equal to x plus some stuff, okay? Now, this is not valid Scala code, so what I'm going to do is I'm just going to comment it out. So this is what we have in math, okay? So an x is called the argument or an independent variable, right? And some stuff is called a parameter, which is sort of assumed to be there in the context, right? So whenever this function is called, it's assumed to be run in some sort of environment where it's known what some stuff is. And in math, it's called a parameter, which is quite different to how it is called in programming, which is what we're going to talk about in a few seconds. Now, f of x, which is the output of the function, is called a dependent variable. Is a dependent variable, right? There we go. And sometimes we also use just the letter y. So y is the same as f of x, and f of x is the same as x plus some stuff. Now I'm going to translate this to valid Scala code. So I'm going to have some stuff, which is an integer, 5, and I'm going to have a definition where x comes in, which is an integer, and an integer comes out, and I'm going to have x plus some stuff, and we're just going to print line f of 4, just for fun. Now, in programming, x is actually called a parameter, which is which is already very different from math. Okay, it is also sometimes called a bound variable. Let me remove the cursor. Let me put it over there. All right. So some stuff is called a free variable, which is not bound to this lexical scope. And in this case, it is bound to the constant of 5, which you see over here. So 5 is bound to some stuff. Some stuff is a free variable in the lexical scope of f of x. Now, the output is called the result, or resulting value, or return or returned value as well sometimes. By the way, 4 is an argument for the parameter x, and math doesn't seem to have a disambiguation there between the x and the 4. I guess the term argument is simply reused. So from now on, we're going to use the programming naming conventions, okay? Let's get to the second point, and the second point is about arity, which is the length of the parameter list, right? So in this case, we have a function with only one parameter, and we'll sort of jump straight into that, right? So what about functions which have 0 parameters. Now in math, functions like this simply don't exist, but in programming they do, right? So let's have an f, and let me comment this out so that I can just reuse the name f. Okay, f, which has an empty parameter list, right? Which means it's a parameter list with 0 parameters, right? And let's say, it doesn't really matter, let's say it returns an integer, which is, I don't know, 5, okay? And so now we can print line f. All right, that's cool, but what about the functions with more than 1 parameter? Okay, so we have already 0 parameters and we have 1 parameter. What about the ones which have more than 1 parameter? Well, in programming, it's nothing special. So let's have a function called plus. It takes an x, which is an integer, takes a y, which is also an integer, and it is equal to x plus y, and we're just going to print line plus, I don't know, 3 and 5, and we should see an 8. I'm already using F5 over here. Let's do 7 and 3. Some real hardcore math here, huh? Let me also scroll down, and we don't need this one anymore. Let me scroll down a little bit more. Okay, so functions with multiple parameters are nothing special in programming, but they are in fact something special in math. There are some dedicated subfields in math, like for example, multivariable calculus, or 3-dimensional graphs, or parametric surfaces, and these are just the few things that come to mind. Also, when we're dealing with functions in programming, we usually only care about putting something in and then expecting some sort of behavior, or at least to get a value back, right? In math, the goal is usually rather different. So in math, usually people are concerned with plotting graphs and having deep discussions about all the possible inputs and all the possible outputs, for example. And it turns out that it's not so easy to have those discussions about multivariable functions. So what you do in math is you use a very cool technique called function currying, and this technique is also present in programming. So this is how it works. So function currying is when you take a function which has multiple parameters and you convert it into multiple small functions which take only 1 parameter. Let's see how this works. So we have a regular multivariable function over here, and let me put this into this line. Okay, so what we're also going to have is we're going to have plus curried, and it's still going to take an x, but now it's going to have a second parameter list, because Scala just happens to support function currying natively in the syntax, right? So we have 2 parameter lists, but the rest is the same. And by the way, I prefer to specify the types, and I sort of forgot to do it here, and Scala inferred it for us, which is kind of cool. Okay, so now also when we call this function, so when we call plus curried, so before we would do 7, 3, and in this case we're just going to do 7, and the second argument is going to be 3. So what the result should be is it should be exactly the same, right? So this is a 10 and this is a 10, and this might be confusing for you, like if you're coming from some different programming language, you've never seen that before. What is actually happening behind the scene is the following. So let's have a function plus curried manually. Right? So what is happening is that an x comes in, and the result type of this function is another function, a function that takes an integer and maps it to another integer, right? And it looks like this. So this integer is going to be called a y, and the body of the function is going to be the same as what it was before. So it's going to be x plus y. So the x is a free variable in the lexical scope of this function, right? But x is a bound variable in the lexical scope of this entire function. Okay, so when we call it, it should look exactly the same. So we're going to say plus curried manually 7, and this second argument is a 3. So what is happening is that 2 things are happening at the same time. So one part of the computation is being produced over here, and the other one over here. So let's do it even slower. So let's have a val called partial computation, right? And it's gonna return another function. Okay. So all we're gonna do is we're gonna say plus curried. Basically, we're just gonna copy the first part, right? Because this part produces the function. Right, so this is exactly the same as this. Therefore, there's an equal sign over here. Okay, so now what we can do is we can print line partial computation of 3. Okay, and now it should be the same. So the 7 is sort of frozen, right? It's sort of fixed, and now we can just add a 3 to it, or we can add a 4 to it, and so on. So the following code is exactly the same. Let me duplicate this line, go over here, right? So we can have print line some curried, I'm sorry, why am I saying some? Plus curried manually, right, was a 7 and a 3. And we can also do the same thing with plus curried, okay? Right, that's of course not a comma. This is the second argument, okay? So we have a 3 over here, and in fact I can just copy this and just replace all of that with it. All right, so now it's fixed. So all of these, they do exactly the same thing. In fact, let me comment out the other print lines so that you can see it better. This one, and there we go. Okay, and also let me remove this empty line and this empty line. I don't like empty lines. So now what a mathematician can do is, instead of having a discussion about two parameters, which is complicated, what they will do is they will just have two separate discussions about two functions with only one argument by basically freezing the first one, right? So they say, okay, the first one is going to 7. What is this function is doing? Well, this function is always just adding things to the 7. So it's basically just one parameter. So it's a much easier conversation. So function currying is a very powerful technique in math, but it is also very useful in programming. However, in programming, not always, but most of the time, it's used for other things, and those things are going to be discussed in the next video and probably even the video after that. And by the way, in programming, function currying is not constrained to have multiple parameter lists with only one argument, right? So we can have multiple parameter lists with multiple parameters, okay? Because in programming, again, we're not concerned about having deeper discussions about functions. So let's demonstrate that. In fact, in my preparation for this video, I used to call it sum. Actually, let me have a sum here and over here as well, everywhere. All right, so this is a sum. So let's have a function called sum and product curried, right? So we're going to take an x as we used to, but we're also going to take an a, right, which is also an integer. And the second parameter list, which is going to take a y as it used to before, but it's also going to take a b, right? And the result type of this is going to be a tuple of int and int. So it's basically just going to produce two things at the same time, okay? So what it will do is it will produce this tuple like this, right? So the first thing is going to be the sum, right? It's just going to do x plus y, and over here it's going to produce the product. So it's just going to be a times b, okay? So when we call it, let's call it with some, no, this one, sum and product curried. So let's say that x is a 7, we can use named arguments here, and let's say that a is a 5, and the second parameter list is going to be 3 as before. I just want to keep it simple, and let's say that b is a 4, for example, right? So 7 plus 3 is a 10, and 5 multiplied with a 4 is a 20, so we see this tuple over there. All right, now let's talk about the elephant in the room, referential transparency. So referential transparency is a property of a function. So a function is referentially transparent if its value, the result of its computation, only depends on its argument. Specifically, it does not depend on the context in which the function is executed or on the time of the execution. If this sounds like gibberish to you, think about a function in terms of Chuck Norris, right? So when Chuck Norris wakes up, it doesn't matter if it's Monday morning or if he had, a really long night, a really rough night with a bunch of drinks or something. He's always going to do 100 push-ups, no matter what time is it, no matter how he feels. And it's the same with mathematical functions, right? So if you have a function like sum, it doesn't matter at what time of day you call it with a 5 and a 3, it's still going to produce an 8, right? Always. So whenever you call it with a 7 and 3, it's always going to produce a 10. Whenever you call it with 5 and 3, it's always going to produce an 8. It doesn't matter at what time. It doesn't matter in which context, it's going to be always the same, dependent only on the arguments, okay? Now, this implies many things. First and foremost, it means that functions in math, they always yield a result, right? And some value, right? And in programming, it doesn't have to be, right? So in programming, sometimes we just call a procedure, right? Just to have some behavior, just to trigger some behavior. Let's demonstrate that. First of all, let me comment out those print lines. We don't need them anymore. Okay, so let's just have a function over here. Let's call it trigger behavior. Okay, and it's gonna return a unit, and it's just gonna print line. Oh, come on, hi. Okay, so and now over here we're just gonna trigger this behavior, and we should see hi. Okay, in fact, even print line itself is a function like this, right? So we just call it like that. We just trigger a behavior of printing something to the console, in this case an empty line. Let's have something slightly more complicated. Let me comment this out, and let's have a loop. So we're gonna have a function, we're gonna call it the same, trigger behavior, right? Also produce a unit. So all we're gonna do is we're gonna go from 1 to 99, and we're going to go for every number from 1 to 99. We're just going to accumulate the sum. Okay, so we're just going to say result equals result plus this number. Okay, and therefore we need to have this variable called result, and before the whole computation, let's just say set it to let's set it to 0. Okay, so over here we're just gonna trigger the behavior, and then we're gonna print out the result, right? So if the behavior is not triggered, then none of this is happening, right? So if we don't do that, then the result is going to stay 0, right? So this is not really mathematical, right? But in programming, it's very, very common. So as you can see, functions in programming, they don't have to be referentially transparent. In fact, most languages, and when I say most, I literally mean almost all of them, don't enforce referential transparency. Some, like Haskell and other languages in the ML family, they try, and they actually get really far was this concept of enforcing referential transparency. But even in Haskell, there are tricks and there are ways to get around this. And we're actually going to see an example a bit later. We're not going to do it in Haskell, but we can actually see, we're going to have an example that sort of demonstrates that. So the problem is that if those constraints, if they can't be enforced, then mistakes will be made, right, by beginner programmers or even by experienced programmers. Programming is not so easy, right? Referentially transparent functions are much easier to deal with and to reason about, but sort of unfortunately, they are almost always in the hands of the programmers. For example, this example right there can be rewritten, right? Rewritten in a referentially transparent way. So even though we have a variable and we're modifying it, we can just bring it down, for example, okay? And then in terms of the computation, we can just return it, okay? And now the type is going to become an int, okay? So now we're going to trigger the behavior, but it's actually not being triggered anymore. It just produces the result. So we're just going to put it over here, right? So the result now should be exactly the same, but now the trigger behavior function is referentially transparent, right? Even though it sort of modifies some state. Let's have another example for breaking referential transparency. Let's comment this out, and let's have a function now, which is going to take a pattern, which is going to be a string, and it's going to produce a string with the current time. In fact, we did this already in another video. So first, we're going to create a formatter, which is going to come from java.time.format. In fact, let me scroll up a little bit. Okay, so format.datetime formatter, okay, of pattern, and now we're going to give it the pattern. This is the pattern that is coming in over here, right? So what this function is going to return is going to be java.time.local datetime.now, and it's going to format it with the formatter from here. Okay, so what we're going to do now is just we're just going to show the current time 5 times. Okay, so we're going to do for each, and in this case we're not going to care about the current number. Okay, so what we're going to do is we're going to print out now, and the pattern is going to be the string. We're just going to want to see the hours, the minutes, and the seconds. And now we're just going to do thread sleep for 1 second. Okay, so we're going to print out the current time, and then we're just going to wait for 1 second, and this is how it's going to look like. So even though we're calling this function with exactly the same argument all the time, and even though we ourselves, we're not changing any state, right? We're not changing any state ourselves. Some state is being still kept somewhere and being changed by something else, right? So even though we didn't do anything wrong, right? This function is not referentially transparent. So we give it the same argument. It produces a value. It doesn't actually return a unit, right? But it's still not referentially transparent. These are the most common patterns for breaking referential transparency. And the next item on the list is totality. So let's comment this out, and let's have a function called square, right? So x comes in, and some integer comes out, right? So it's just going to do x times x. This is how you square things in programming, okay? So this function is total because it's defined for all the possible integers, right? So all the possible integers will come in, and it is always going to work. So this function is called a total. So let's just say total function, okay? And let's have another one. Let's have a function called division, okay? So x comes in, y comes in, integer comes out, and it's just going to do x divided by y. Now this function is not total because division is not defined for 0, so you cannot so y cannot be 0. But what you usually do in math is you sort of cheat, right? So you go in and say, okay, so x is going to be, so they use this other notation, the e symbol. They would say x is an element of ints, or they would do z, right? And then say, okay, y is also an element of z, which is, you know, all the integers except for 0, right? So in math, you would just sort of write it on the whiteboard, and then it is assumed that nobody in their right mind is even going to try to call division with a y of 0. Okay, so they sort of cheat, and they make this function total again. So basically, all functions in math, they are total, or they can be made total. Well, in programming, it's not the same thing, right? So in programming, even if you have a function that sort of looks total, it can still die a horrible death because, you know, you run out of memory, or you know, an exception is thrown, or something like this. I don't know. In fact, let's just print line. Hold up. Let's print line division of 1 and 0, and it's just going to explode, right? So this is a concept called exceptions. So it doesn't actually explode, right? So but if it's not handled, then then this is what is happening. So basically, you cannot reason about this function in a referentially transparent way because an exception can be thrown. All of this brings me to the last point: the substitution model for procedure application, which is a model of computation, or which is an algebra, which is a a small set of laws which help you to think about a computation. In fact, a referentially transparent function can and should be defined in terms of the substitution model of computation. So a function is referentially transparent when you can go through the whole program and rewrite every call to that function with the value that it computes. We actually have an example of this. Well, we have many examples of this, but I would like to go back to this example over here. Let me comment this in again, just so that we have a bit more of syntax highlighting, right? So look at this. It says partial computation is the same, right, is equal to this code over here, right? So everywhere in the code where we use partial computation, I can just go and take the value that it computes and just put it in there, and it should be exactly the same code, and in fact it is. So this means that partial computation, that this function is referentially transparent. And also, just by the way, since it produces another function, this other function that it produces also just happens to be referential transparent, right? But this goes a bit too far. The point is that this function is referentially transparent. It just kind of happens to also return another function, so it kind of, inception. Now, because all mathematical functions are referentially transparent, they can be reasoned about in terms of the substitution model of computation. And this model of computation is one of the, if not the simplest models of computation out there. And unfortunately, we can't always use it in programming, as you have seen. It's way too easy to break it. Now, there are certain styles of programming which promote this way of thinking, specifically the substitution model of computation. The style of programming is called functional programming, and the programming language called Haskell, the one that I mentioned before, is one of the functional programming languages that is as close as possible to this model. Now, I'm a big proponent of functional programming, which is also why we're going to have many more videos in the future about it. But you have to be really careful. You can't deceive yourself, because the substitution model of computation is just there to help you to reason about your program, right? But it's actually not how the programming language is actually behaving. So the compiler, it doesn't actually go and literally rewrite your source code like this, right? It actually uses a different model of computation called the environment model of computation, which is a topic that we're going to discuss in the next video, or maybe the one after that. So because it's a different model, it is hard for programming languages to enforce the substitution model of computation. And also, not all programming languages want to do that, because this would constrain programmers almost too much. Well, I'm only saying too much because a lot of programming languages do this on purpose, not because it's hard, it's just because they don't want to. Furthermore, the journey to functional programming only begins with the substitution model of computation, but it doesn't end anywhere near it, which is something that we're also going to discuss in the future. Now, as you've seen, there are so many differences between mathematical functions and functions in programming, which lets me to believe that maybe it wasn't such a good idea to reuse the word function when it comes to procedures or subroutines in programming. So maybe, just maybe, we shouldn't have used the word function, which sort of, again, as I already said, contributes to this stigma that programming is all about math. Having said that, we've seen already in quite a few occasions that mathematical functions are very easily modeled with programming procedures. Allow me to end this video with a rhetorical question. Let's say that you have a perfectly referential transparent function, right? But it just happens to take a long time to compute. Does it still comply with the substitution model of computation? Well, I mean, technically it does, right? But how useful is that? I mean, I'm sure in math, it's still useful, but it looks like we got 99 problems, but math ain't one, which is a joke that I made already in a few videos back. Okay, so let me finish this video with this one example. Okay, so I'm just gonna print out a very big number, right? I'm gonna print out, and actually let me copy it from a script. There we go. Okay, so this number happens to be the Fibonacci of 100. And let me remove those print lines from over here, right? Okay, let me scroll back down. Okay, so now this big number is a Fibonacci of 100. And if we have a definition of Fibonacci, if we implement Fibonacci in a naive way, which is the the math way, but math doesn't really care about the execution. So in math, it's a perfectly valid definition, right? So it's basically just rewritten in Scala now. So Fibonacci is defined like this. So if n equals 0, then we're going to return a 0, and I don't like the space here. Else if n equals 1, we're going to return a 1. Otherwise, we're going to do Fibonacci of n minus 1 plus Fibonacci of n minus 2. Okay, so this is a perfectly valid definition of Fibonacci if we use small numbers, right? So let's do print line Fibonacci of 0, and just a few examples: 1, 2, 3, 4. Let's also have 5 and 6. All right, so as you can see, it works. Let's actually do 7 and 8. 7 and 8, right? Because I want to see the 13 and the 21 over there. Okay, so this is a perfectly valid definition of Fibonacci in math, but in programming, it's only a valid definition if we use very small numbers. So let's go back to this code over here, this one. Okay, so we're printing out this. Now, in theory, it should be the same as printing the Fibonacci of 100, right? The model of the substitution model of computation. It should be valid, right? So it's a perfectly referentially transparent function. Now we see this print line over here, right? But we're not seeing this one. In fact, we don't see the second line of hyphens. The program is surrounded was a list of was a bunch of hyphens, and it should end with a bunch of hyphens. But as you can see, my CPU is up, so it's still computing the Fibonacci of 100. And I'm sorry to tell you, but you're not going to stay here long enough to see what it's going to compute. All right, so it's been Vlad. I hope you liked this video, and if you're new here and if you want to improve the developer inside you, then subscribe, and yeah, that's it. Cheers, take care.